Just about ready. All right. Any particular questions that we want to put on our plan for today? Any particular exercises that we have to do? I have some things I'll show you, but maybe while you were studying, you have some stuff that you were stuck on that you want to hear about. Anything? Yep.
Worksheet 5.
Worksheet 5, yeah. Which question? All of them. Okay, cool. Anything else? Tutorials, exercise sheets, something you saw online? Yeah?
That's number 3.
Cut number 3?
Question 3A.
3A. So let's just put that over here. Cut 3, Q3A. Okay. Anything else? Just take a look at what that is. So I think what I'd like to do to start is to kind of pick up where we were last time. So that's basically just doing some more stuff to do with sequences from the definitions. And then we jump on to we'll start jumping around after that to anything from the course. Yes?
So it's exercise sheet 5, question 3I.
Okay, so exercise sheet 5, Q3I. Okay. Let's see if I have that right here. So 5 and tutorial 3, I'll just put that as well, just so we can kind of put things in a logical order. Okay, so 3A was this question about subsets of the natural numbers and kind of countability and stuff. Okay, cool, we can talk about that. And exercise sheet 5, question what? 3I. All right. 3I. Oh, okay. Huh. Let's see. I suppose you were told for your test that it's tutorials 1 through 5 and exercise sheet 1 through 5? Is that right? Or is it exercise sheet 1 through 4? Does anyone know? It's an important thing to know to the test system. Hey.
Exercise 1 through 5.
As well. Okay, good. Okay, so this one's kind of like series, something about series. You don't need to write this down. This is just for me. This one's about countability. Okay. Any other specific questions that come to mind that you saw while you were studying that you really want to see worked out in detail? Anything? Okay, if it comes up, just put up your hand at any point. All right, so last time, so we'll do a little warm-up. Okay, / last time. We talked about the definition of a sequence converging in detail. What are we going to write there? Well, I hope by now everyone knows the definition. We'll still write it up, but I hope by now we've had a chance. Is anyone unhappy with the formal definition of a sequence converging to a real number? Because we can talk through that really briefly, but we definitely need to know that for the test. It's super important. Okay, so last time we had, I don't know if you want to write this down. You don't really need to write this down. It's just, so formal definition of an converging to some real number a. Okay. And so the question that we're going to warm up with is just what if I give you an? I think this was on the one of the exercise sheets or something like that, and I give you something like this. Okay. And maybe from first year calculus, you look at this. So we can write from first year. We know that basically it's kind of obvious that an is going to go to 0, okay? Unless I've written something down incorrectly, but so the denominator gets big, whole thing gets small, eventually goes to 0, everything's positive. So we have a good feel for what's going on. All of the terms are positive. There's some weird, irrational kind of denominators, but the idea is that it's going to converge to 0. Now, how do we prove that? You know, in a sort of a rigorous, real analysis kind of way. So we're going to prove from the formal definition. So how do we do that? So we'll just write it up here really quickly. Just so you recall, that we're saying that for all epsilon greater than 0, there has to exist a natural number such that when my little n's are greater than that natural number, it implies that an minus a is less than epsilon. And I would write this, okay? So I'm not really writing this out in detail because I hope by now we've gotten a little more comfortable with it. But this really is totally rigorously correct what I've written, but I haven't used long words and pictures and things like that. So I hope by now we're sort of getting into the feel that what we want to say is that the sequence gets close to a real number, and it doesn't just get close to a real number once or twice, it gets close to a real number for all infinity of the terms as we go towards kind of the tail end of the sequence. So past some point in the sequence, all of the terms, all infinity of them, every single one is very close to this number a. And then we talked about what do we mean by being close to? We mean that the absolute value of the difference is less than whatever, for any number that I can pick. So just saying through it again, we play the game, you give me some real number, you give me some positive real number, and I can find a point in the sequence such that whenever, for all the terms past that point, so I could even put a for all here, but really if you check, I'm just saying that for any n that's greater than that point in the sequence, all of those terms obey this inequality. And then we play the game more. You pick a smaller real number, I can still find a point in the sequence such that all the terms are closer to a than that real number, and we keep going smaller and smaller, and so we get that kind of intuitive idea of the sequence converging to a. Okay, any questions on that so far? Okay, so how are we going to apply that to this sequence, okay? So again, I was sort of showing you last time, it's always good to see if you can rearrange the problem that you're trying to solve into something that's much easier to look at, something that looks more like something you know how to work with. So we just kind of write down, without saying anything formal yet, we just write down what we're looking at. So if we want to show this goes to 0, I need to show that this, n plus, what did I say, 3, minus 0, and we haven't really said what epsilon is, or if it's true for all epsilon or anything at this point. We're just kind of investigating this object that we see appears in the formal definition. Because 9 times out of 10, you write this down, you're going to find a way to simplify whatever you write down in here. You're going to write down the sequence, and you're going to write down that limit, and you're going to see if you can rearrange that object into something easier to work with. Okay. So what am I going to do here? Can anyone kind of walk me through it? What's going to help me at this stage? So, any ideas? Okay, well, obviously, we don't care about 0, and all of these things are positive. So obviously already, I can just say that really I care about this, okay? The absolute values don't cause me any problems. I just have a 0 there, so I don't have to think about it. So I'm just looking at that inequality, okay? Now, what can I do here? How can I make this more useful to work with? Any ideas? You don't have to be shy. We're all friends here. So what should we do?
Can you try like comparing it with comparison?
Absolutely. Okay, so one thing we think about, do I know things that are smaller than or bigger than this that are going to help me? So your favorite ones are always like 1 over n. You have stuff like this, 1 over n squared, okay? The problem here is that, well, my favorite one that I like to compare to is 1 over n. Okay, we always know how to work with that. Just to give you some more things for your notes, you don't have to write this down, but this is just kind of, just so you remember. We always have stuff like this. You know, this is always less than 1 over n squared, which is always less than 1 over n. So these kind of inequalities are always useful to us. Why does this work? I told some people who weren't here last time. I have a sum of 2 positive numbers in the denominator, so without even doing any kind of complicated inequalities and dividing and things like that, I just look at this. 2 positive numbers added together is always bigger than one of the 2 positive numbers, okay? So if I have something bigger in the denominator, it means that the overall thing is smaller than if I just take one of those numbers. So I can always just throw away that 3 and I get to here. And then this one's always bigger than that, which means 1 over this one is always less than 1 over that. And then this one we know how to work with the Archimedean property. Okay. The problem is square root n is less than n. So 1 over n is less than 1 over square root n. So I'm not sure that I can use 1 over n here. Maybe there's something else I can compare to. But you do run into this problem for this particular thing. So what else could we do? Could I simplify this in some way that helps me? Something? Square root?
Yeah, maybe you can try to get rid of square roots. Maybe.
You want to get rid of square roots? Okay, let's try that. So these are good ideas. Whenever you're trying to solve these problems, you try this stuff out. You just write down the object that you're looking at, and you say, what 2 or 3 things do I know? You never want to think of more than 3 things. It's, you'll get lost. So we want to get rid of square roots. So 1 over n plus 3 is less than epsilon squared. Okay. Now what can I do? Can maybe rearrange a little bit. Okay, a little more. So that also implies that 1 over epsilon squared is less than n plus 3. Okay? And that also implies, so now it may seem like I'm going too many steps ahead, but we'll see why this is all sensible. Less than n. Okay? Could this be true? Could we possibly make that true? Yeah, we could, right? This is just some real number. Doesn't really matter. I don't think about it too much. It's just some real number. Okay. And, are there natural numbers that are bigger than just some real number? Yeah, there are. That actually looks a lot like our Archimedean property. Okay. So this problem is actually really similar to when we wanted to prove this. Okay. Funnily enough, even though it looks really different. Okay, at start. When we start rearranging things, as long as we kind of let go of our fear of this looking kind of messy, we can rearrange this kind of problem into something where we just use the Archimedean property. So I'll write it out formally, don't worry. We're going to write out the formal proof and see exactly how carefully we can say this. But kind of one of the lessons of these things is like, we feel comfortable with 1 over n, we feel comfortable with 1 over square root n, and as soon as we add a little thing, we might get thrown off, but let's not get thrown off. Let's just go through our 1 or 2 things that we're checking. The general strategy is always write down this inequality that you want to work with and try play around with it. Try simplify it into something that either you know is less than something that you've already studied, or is covered by some broad property like the Archimedean principle. And remember, there aren't that many broad properties. It's almost always Archimedean principle or the triangle inequality are the kind of things that we use. All right, but enough words. Let's just write carefully exactly what we did, because we may be a little lost now. So we need to prove from the formal definition. So let's write out a formal proof showing that we really did do enough work now to show that we've proved this result. Okay, so formal proof. Okay. Suppose we are given epsilon greater than 0. Okay. Then okay. So then by the, and I may need help spelling this again. I didn't do my homework, which was to stop misspelling Archimedean. The Archimedean property, or principle, I don't know. There exists an n in the natural numbers such that 1 over epsilon squared minus 3 is less than that capital N. Okay? Do you see also if we hadn't done this step at first, it would be kind of impossible to do this? I mean, like, how would you kind of just staring at that sequence know that you needed to write down this? This would be very difficult, I would say. So you always write down the inequality you want to study, then you rearrange it, okay? Then you write your formal proof, okay? So we know this capital N exists, and then we just have to say, then, for all little n that are greater than that capital N, it's true that 1 over epsilon squared minus 3 is less than that capital N, which is less than that little n. Okay. Okay. And this, if we just rearrange it, is which implies that, well, we'd add 3, and then we'd square root, and then divide, and we end up with square root of n plus 3 is less than epsilon. Okay? And just that last step, just to be clear, I added 3 over to here, I square root the whole thing, and then I divide again. I just undid the work that we did when we were simplifying everything. If you don't believe me, go and just check. Okay, and you know, just to be clear here, you wouldn't write this in a test, but you can definitely say, you could at this stage, if you really wanted to check for yourself, you could say, well, that really was my AN. This step is unnecessary in the test, just to be clear. All right, unnecessary for your notes for test / exam. Okay, but just so we really know. Okay, so is any questions on that? That was kind of a warm-up question in a way, but may have been slightly more complicated than things we did in the past. Okay. Now's a good time for questions on this, otherwise I'm going to erase it and go forward. But again, the lesson was the same. We know we need to somehow prove something about this inequality, and we need to find that capital N. So we write down the inequality we know we're going to end up having to prove something about. We rearrange it into a more useful form, and then we ask ourselves, what things do I know that can help me show that this inequality is true? If I can show that this other inequality is true, and everything I did to rearrange this into that inequality kind of goes both ways, then I don't have a problem. I can work backwards and get what I needed. As I said, it would be very hard to write this down first, but it's very easy to turn this into that and then realize what you need to do. Okay. All right, so, and then again, you might ask yourself, how would I know that I needed to use the Archimedean property? Okay, that's a good question. Well, rather think about it this way. We haven't covered that many things. We've shown you how to compare some sequences to other sequences. So almost always you're going to be comparing to 1 over n, okay? Or some simple sequence that we already did. Or you're probably going to be using the Archimedean principle. Sometimes we use a triangle inequality. And really after that, there aren't that many things that we've covered. So don't feel like, wait, how do I know what possible tools I can use? We just make a list. We've got like, say, 3 or 4 tools. You're going to write down the inequality you're interested in. You're going to rearrange it into another form and check which of those 4 tools that you can use, and then kind of work backwards and write down a formal proof. Okay? All right. Last chance for questions, or we go on to the next one. Anything? No? By the way, so we are doing a long session today, so do you want to break, say, at 6:30, like 5 minutes, go to the bathroom, stuff like that? 10 minutes? 5 minutes? 5, 10? We'll discuss it. Okay. All right. Can I ask a quick question? How many people went to Murray's thing yesterday? Is anyone there? Okay. there's a few people. Did he do this kind of thing? He did it yesterday. Okay. Do you know if it was recorded? Couldn't guarantee. Okay. Do people want to see this again then, maybe? Okay. Sorry to people who saw it already, because that was what I was going to do next. Okay. So maybe I'll describe it slightly differently than he did, because that could be useful. All right. Suppose an converges to some real number a, which is not equal to 0. Okay. Show. So this was something I put on the Rula announcement. Show that 1 over an converges to 1 over a. Okay. Now the reason I want to do this one is it's a little bit different from the other sort of axioms that we wrote down, the sort of rules that you have for sequences. You saw that if you add two sequences that converge, then they converge to the sum of their limits and stuff like that. This is probably one of the harder ones because you have to use a technique that's a little bit different from everything else we've done. So what's my first step? So this is my rough work. Again, you don't write rough in the test unless you really want to emphasize something, but you can just do it at the back of the book or something. But first you do rough work, unless you know how to prove it by heart right away, but it's always good to go here. All right, so what's the thing I have to care about? I have to care about this, right? This is the inequality that's going to cause me problems that I need to resolve. All right, so we'll leave that definition there. So what am I going to do first? I'm going to simplify it, right? Just like every other sequence problem that we do. Got to turn this into something easier to work with. All right, so one of the obvious simplifications we always do when we have fractions, we're adding together, common denominator, right? So we're just going to have, this is basically equivalent to a minus an over a times an, right? Hope I did that right.
So do you not say it's equal, right?
I could say this is equal to this literally, but what I want to do is I want to say it's equivalent to that statement. If you just want to save time and you just want to say this is equal to something else is equal to something else, that's fine. It's definitely true. Okay. Whatever allows you to simplify it. I'm just saying it this way because, like, I don't know. I have extra space and extra time, so it's not. For me, it's sort of logically looking good to me for the purpose of instructing.
Say it's equal to.
Sorry? If you said this is equal to, this might get a bit confusing. Okay, like depends how you lay it out on the paper. So I'm being a bit pedantic now, but it's important to. So this whole statement is not equal to this whole statement. Okay, that doesn't make sense, right? You know, this is a logical statement, and this is a logical statement, and saying they're equal doesn't make sense. Now, if you did something like this, if you're on your paper, you're like, this is equal to this, and then you're telling me that this is less than that, then that's fine. That makes sense. Okay. If you just put the equals here, it also might read funny down the paper. This less than that, is this now equal to this? As I come kind of following the normal convention. So anyway, just lay it out sensibly, and then it's fine. But if you're talking about logical statements in a proof, you want to say equivalent. Okay. All right. So looking at this, we already know that we can probably work with this numerator, right? Why? Because we know an converges to a. And we know then that in the proof of an converges to a, I'm going to get something, or in the definition, sorry, I'm going to get an absolute value of an minus a is less than epsilon somewhere. Okay? So that part I can possibly already see that I might be able to do something with that, okay? But what's tricky is this. How do I deal with that, okay? If this real number, a, in the denominator doesn't matter. We've seen that I could even write this in an equivalent form that maybe makes what I'm saying a little more clear. This is really equivalent, okay, I'm just multiplying by minus 1 through an absolute value, always allowed to. This is really equivalent to 1 over mod a like this, okay? Okay. I don't know if this is useful for you to write down, but This is really true. So this thing, we have an inequality that might help us be less than something, okay? This numerator. We also know that when I multiply by just some real number, I can still usually just always deal with that, okay? We've seen that if I know that this is true, I could just choose a different I can choose an epsilon. Is it an epsilon I choose? I can choose an n carefully so that I get the right epsilon, even if I have this real number in front multiplying this, okay? But this part, it's not clear what to do with, right? This is the tricky part, this denominator, okay? Because we need to look for something, so I'll just write out now what I'm saying. Let's write this out carefully for your notes. Since an goes to a, I have the tools to deal with and then we'll just say times k for any k element of R. Okay? Okay. But what about okay, so what about this? How do I deal with that? Yep.
During the test, I was supposed to prove the elements are proven in class.
Usually not. Yeah, so my understanding of the rules for the course, and pretty much any math course, is anything that was proven in class, you need to know, you have to memorize the definition, you have to memorize the results of the theorem, because you can't do anything if you don't know the definitions, you don't know the theorems. But you don't have to memorize the proofs, and you don't have to reprove things. Okay. Now, if they give you as a test question, please, well, I think they've agreed not to give you a direct proof from class, but they might give you a modification, right? And in that case, then you need to know how the proof works. If that makes sense. When I say a modification, that's probably scary to hear. What I mean by that is, what's a good example of something like that? They might have proved for you like the properties of the infimum and the supremum and stuff like that. And they might have said in class, like, prove that if the they might have said, like, if the supremum is an element of the set, then it is the maximum element, okay? They might ask you to prove that. Okay. And it's also going to be based on length. So, they're not going to give you a proof that's like 30 arguments long, like all these equivalent statements with lots of lemmas and stuff like that. That's unreasonable. But if the proof is like 2 steps, like do this one inequality and apply this other property, they might ask you something like that. So that's also, but the general rule is proved in class, you're allowed to use it, state that you're using it. That is often worth marks and at least helps the person marking see what your argument is. But yeah, you might want to also check on tutorial stuff, because some courses they say, if we proved it in the tutorial, it's fine. Other courses they say, no, only proofs from lectures are allowed to be used without being reproved. Yeah. But for example, like if they tell you, use the definition of a limit to prove that 1 over n goes to 0. Okay, you got to prove that. You can't just say, by in class. We saw that in class a few times, so yeah. If there's ever any confusion, just ask during the test or the exam. All right, so we know we need to somehow kind of make this whole thing less than something that we eventually want to be epsilon, right? We know how to make this less than things. We use the definition, less than something. And we know how to make this times any constant less than something. That's what I kind of wrote here, Okay, we know that I can take this times any constant, so in particular that constant. But this denominator that kind of depends on little n, and make that a little more clear, is not immediately obvious what to do. Okay? We also want to make this less than something. Okay? So let's study how to do that. We need to know how to find, or how to let's just say how to make 1 over an less than, and I'm just going to pick some letter b for some useful b. And we'll figure out what b later. We'll figure out what b to choose later. Okay. So we need to know how to make this kind of thing less than some real number. And we'll figure out what that useful real number is later so that we can kind of tie it all together. This may seem a little bit out of left field now, but once we put all the pieces together, it'll start making sense if you're getting a little lost. But please do put up your hand if you're not sure what's going on. Okay, so this, this is equivalent to trying to study this, 1 over b less than mod an. Okay? I just divide and multiply. Okay? And this is really the key. Like, we have we have a lot of tools to show that absolute value of something is less than something, and then we can kind of put these things together in useful ways where we kind of work backwards and figure out what we need to do. But we don't really know how to show that something is less than the absolute value of this an. How do we get that less than? How do we study things on this side? Well, the answer is the reverse triangle inequality. Okay? And I did say this in the Vula announcement. Okay? So let's just do that quickly, and we'll see how it all fits together. So, key. The reverse triangle inequality remember that tells me that, let's not use A and B, let's use C and D. C minus D is less than or equal to, so this is a reverse triangle inequality, okay, for all C comma D, any real numbers. We don't have to worry about whether they're positive or negative or rational or anything like that. Helps me study problems like x less than or equal to, okay, something less than. Whenever I need the less than absolute value of an, the reverse triangle inequality is going to help me. Okay? And the reason why is kind of, you can almost see it in the structure here, is, well, do you see any absolute values around these numbers? No, they're over here. So if I'm given something like this, I can go over to here. And now I have absolute values. why I put this all together. I know it's getting a bit long, so we might lose the kind of train of logic, but let's see, did I ever, okay. All right, so we just need to be a little careful about what we put in here. So we know, because AN goes to A, we can find N such that is less than, and we'll just put some number here, maybe capital C. Okay. And really this is for all n greater than that capital N. Okay? All right. And then that implies, I just need to check that I do this the right way. Yeah, okay, well, let's see what happens. All right, so then using the reverse triangle inequality, I get that AN minus A is less than AN minus A is less than C. Okay? So do you see we're starting to build up an inequality chain where actually this absolute value of AN appears? Okay, and we needed to look for something where we had something less than absolute value of AN. So how do we start kind of solving for absolute value of AN? Well, you know that this is equivalent. If I want to remove this absolute value when I have absolute value of something is less than C, less than C, okay? Actually, let's just put it up here instead of me yelling down. How do I remove this absolute value? I write minus C is less than mod AN is A, which is less than C. Okay? See? Okay, we've said that before, that if I have an absolute value less than a number, it's equivalent to saying that minus that number is less than what was ever inside the absolute value is less than C. Okay, that's how I remove absolute values. If this number is positive. If it's negative, you have a problem. Because how do you have a positive number? Remember that this is always positive. Okay, so we're starting to solve for an inequality that involves that mod AN. And what's the last thing I need to do? Well, I just want mod AN, so I gotta get rid of this. So I want to add this across the whole. So let's just show that. All right, so that's equivalent to saying, and I actually don't care about this part anymore. So I won't say equivalent, I'll just say that implies that mod A minus C is less than AN. Okay? Okay, we haven't decided what C should be, but we're just kind of looking at this. Okay, and remember, well, we don't want C to be equal to this, because remember, we want to we want to use this to kind of conclude that 1 over an, mod an, is less than 1 over mod a minus c, right? Okay. We want to go back to something about this, because remember in our original problem we had this in the denominator, and we were asking how can I find an object that is just a constant number that's greater than this, okay? Well, this better not be negative, this whole thing that I just divided by, okay? Sorry, we're wrapping together a lot of logical little tricks, but let's just agree that if we originally wanted to find a number that's bigger than 1 over mod an, when I do this last step of kind of working backwards to get to what I wanted, I managed to isolate this thing that I wanted on its own, and now I get the one, I just divide over to get what I was originally studying. But to do this, when I divide this over, this better not be negative, this number, okay? Because if I divide this over, then this inequality flips and the whole thing's messed up. Okay. So why don't we just choose something now? Okay. And this may seem a bit magical, but remember, this was done like 100 or 200 years ago. People have refined this a lot. Okay, so I'll just write that. To do this, we need mod an minus c greater than 0. So choose, or I'll write this at the bottom. So let's just choose something that makes that greater than 0. So choose c equals mod an over 2. Okay? Remember, we didn't choose c yet. How did we get c? Where did c come from? Let's just check that one more time. We were using the fact that an converges to some real number a. We said that since an converges to some real number a, for any epsilon, there exists a capital N such that this holds. The c that we're using is sitting there, okay? So we are, remember, trying to prove something about 1 over an when we already know that an converges. So since we already know that an converges, this definition must hold for any epsilon. So we're going to pick a useful epsilon. I used c instead of epsilon. There's just some real number. I used c so that we didn't get mixed up with the epsilon that we're using for 1 over an. Okay? So just to say that one more time, we want to prove something about 1 over an, and we want to bound it by something that involves epsilon. Okay? But we also know that an converges. So for any real number, I can pick a real number, I can find a capital N such that this is less than whatever that real number is. I called that real number c, okay? To make sure that we don't mix it up with the other epsilon that we're using. And now I'm saying let's pick a c. Let's pick a c so that we get this inequality, okay? Because I want to find 1 over mod an less than some real number. So I don't want this to be negative when I divide by it, so let's just pick a c that makes sure that this is positive. Are we happy that mod an minus mod an over 2 is still going to be positive? This is always positive, and when I subtract half of itself, I'm still positive. I could have done 1/3, actually. I could have actually put any number in this denominator as long as it was greater than 1. But let's just choose 2, because they did it in the textbook. All right. So let's start putting this all back together, because we've done a lot, okay? But really the lesson of this whole story was you encountered this kind of object and you were like, how do I get that less than something? Well, it's the same as finding something that's less than that object in the denominator, and how do we get something less than mod an? We might need to use the reverse triangle inequality, okay? And we can, when you go study your notes, you'll see how that all fit together. So let's now start putting the whole proof together. And I might just write here, I'll just write here a little summary of what we did. Brief summary. Since an goes to a, okay, there exists an n element natural number such that 1 over, maybe I don't need to use so much space, 1 over mod AN is less than, and what happens when I plug that in there? I get 2 over mod A. That's really all the work we just did, is that summarized. We said that since this sequence converges to A, there must be a natural number such that, sorry, I'm being sloppy, it's very bad, such that for all n greater than that capital N, maybe I can write that a little more clearly. Sorry if this messes up your notes. If you can slot in the for all n greater than somewhere, such that for all n greater than capital N, 1 over mod AN is less than 2 over mod A. Okay? That's what we just showed. And remember, this is just some real number. Yep?
In class, that was just a lemma that was proven.
Okay.
So can you just state that? And say
Sure,
that-
yeah. I don't think you'll be asked to prove this
Okay.
directly in the exam, but the thing I really wanted to talk through was the method of, because sometimes I produce this, okay, and I prove it that it's true, and then you might ask me, what if I have to do something slightly different? And it's like, I don't know. So we want to, even though it's a lot to sort of say in words, I want to generate these notes so that if you go back over them, you say, oh man, how do I do stuff when the inequality is on the wrong side? And you'll know what I mean when you do lots of examples. You're like, oh, I can always go to the right. I can always go to the right with the triangle inequality. What happens when I get into a situation where I need that mod something, I need to find a number less than it? Okay, that's always a hint, do the triangle, the reverse triangle inequality. But yeah, definitely. If you had this as a lemma, perfect. Just, you can state that. But we'll see now, we're going to do a tutorial question where this would be a good example of how the test could go. We'll do a tutorial question that's almost exactly the same. And yet, like, maybe we don't feel confident to do it because suddenly we get to this point where we're trying to bound something like this, and it's like, how do I do that? Because now my lemma may or may not apply, depending on what's inside of here. I think in the tutorial question it's fine, but there could be something slightly different. Yeah. Okay. So I'm not sure if you're all convinced, but this is what if you recognize it from class, then you're probably very convinced. But yeah, hopefully we're either partially convinced, or maybe you can ask a question now if you're not sure. But basically what we've worked towards is showing that if AN converges to A, we can do this. Okay, and this choice wasn't really magical. We could kind of reason it out. It may be a bit much to ask for in a particular test, but we can reason it out. All right, and then we'll just do the last step, right? I think we've got enough now. All right, so the final proof. So formal proof. Okay, and we were saying that suppose epsilon greater than 0 is given. Okay, then there exists an n1 n such that and then we have to think about what this is. I think we just choose it to be something like 2 mod A epsilon. I think it needs to be squared. Oh, we'll see. Okay? So why is this true? This whole thing is just some real number, so we can just write, because AN converges to A. We know by the definition that for any real number, I can always find an n such that, and again, I always leave it out, that n greater than n such that n greater than n implies this. It's very, very important. It's all of the n's implies this, okay? Is anyone lost at this point? We're saying from the definition up there, since an converges to a, I can just pick this real number to always be bigger than this absolute value for all little n's bigger than some, please put the 1 there, okay? Bigger than some capital N1, okay? Also, there exists an N2 such that n greater than N2 implies that 1 over mod an is less than 2 over mod a, okay? That's what we just showed, okay?
The second line of the common proof, are you multiplying by the sign and
The second line, up here?
on the right?
Yeah, this is an epsilon, sorry. So suppose this epsilon is given, and then that epsilon's there. Okay? Now choose, and this is this max argument you've seen. Choose capital N equal to max of the set containing N1 and N2, because I want both conditions to be true. Okay? So n greater than capital N implies both conditions. Both inequalities, let's say it that way. Are true, which means, okay, that 1 over an minus 1 over a, which is equal to 1 over an minus a over an times a. Applying the first inequality, we get, well, let's do the second one first. Okay, so we get 1 over mod a squared. In fact, there's a 2. Mod a n minus a. Okay. And did we make the right choice here? Yes, we did, which is less than 2 over mod a squared. Mod a squared over 2 times epsilon, which equals to epsilon. Okay. So I wrote that out in more detail than you'd need to write in the test or in any exam. We would all believe you if you kind of showed me this inequality and you showed me the other inequality, and then you just wrote, now I know this is less than epsilon. I believe you. I know that you can do that substitution. But I wanted to write it out in detail so that we can just talk about it in case it's unclear. So just to talk through it a little bit. This is where we started, way back at the beginning. We said we wanted to show 1 over an minus 1 over a is less than epsilon once we're given an epsilon. We're given an epsilon at the start. Okay? So we simplified it, and we said we can just do common denominator. And then we said once we simplify it, I have this one inequality here that we spent a lot of time working on using the reverse triangle inequality to deal with this 1 over mod an. And we said that 1 over that mod an, which is in here, remember the absolute value of the product is the product of the absolute values. So I get rid of that denominator, that part. If you look carefully, I just removed that. It's gone. And what did I do? I multiply by this. So that's that 2 times mod a squared, because there was already a mod a there. Okay? So that's me using this inequality to go from here to here. Okay? And then now what do I have left? I just have this in it, this absolute value, an minus a, And I said that that's going to be less than this object, which, again, you could ask, how did I know to do this? Well, I kind of thought ahead because I've done this before, but in reality, you would kind of put like a capital B there, and you would just figure out what does that capital B have to be to cancel everything out so that you get a nice epsilon. They've also probably told you that if you end up with epsilon times a constant, that's fine. You're done. So if you do that, if you end up actually at this step, and it didn't cancel, but you just had some real number times epsilon, that's fine, you're done. We know that at that point you could reorder the proof to, or you could define a new epsilon to get everything to work. Yeah, and then so because I chose this in the right way, it all cancels and we just get epsilon. Are there any questions? We did a lot there. Okay, yeah?
How did we end up with absolute probability?
This one. Which one? This one or that one? This one. Okay, that one came from this inequality. Okay, so I actually just took that mod an minus a, and I removed that, and I just put in that. Do you see? And how did we choose this? This just came from an minus a converging. From an converging to a. Okay, so right at the start we just said, say we're given an epsilon, there exists a capital N1 such that whenever little n is bigger than that n1, this is true. And how did I get this kind of thing here? Like I said, I kind of thought ahead because I've done it before. Does that make sense? Does that answer your question? Okay. So this kind of whole thing here just came from this line. Okay. You had a question? Oh, cool.
The 2 over the one before what she just asked isn't from the other one.
Exactly. It's from right here. You see. So I could have maybe I could have kind of spread this out a little, made it more clear. But are you still unhappy? Do you see? Yeah. So we have, if I could kind of like, maybe I could just write it quickly instead of just pointing at stuff. Just over here, I had like an minus a over an. Okay, right. I can really think of that as 1 over mod an times something, right? And then I just apply my inequality to that, right? Okay, you don't need to write that down, but that's what I did. Okay, any other questions at this point? Okay, so this is kind of a more fancy proof. It took a lot of effort, but it gives us an opportunity to get confused and then ask questions and kind of really disentangle what we're doing. The point was we started here, we got to here, we knew how to do stuff with the numerator. We may not exactly know what to do, but we at least have done lots of problems like that. But we may not have done lots of problems that involve this denominator. And so the answer is you may need to use the reverse triangle inequality. Something we may be less familiar with. Okay, so if there are no more questions, let's move on to an example. Yep?
So that mod squared over to epsilon, do you choose that?
This one.
Yeah, you choose that based on the
I chose it exactly just to make it cancel. Do you see how this cancels that? And I really wouldn't know how to choose that ahead of time. Again, in the interest of time, I try to show all of the sort of steps, like I left the C undetermined and stuff. In the interest of time, I kind of jumped ahead a little. In reality, if you were trying to figure this out, right here, when I'm doing this, what I would probably do is I would put like K times epsilon, or I would put capital B times epsilon, just some undetermined real number. And I might not even have chosen that C yet, except I would have just remembered that it had to be a certain thing to make something positive when I was dividing. But I really might have written the whole thing out and looked at it for a while and tried to figure out what to choose. So it does seem a bit magical, but that's how it works in
And
practice.
also data, how do you know how to take the max?
That's a common technique. So that's one where it's a little bit less magical. It's like, I'm looking at this, I see that an appears twice. Unless I can eliminate it immediately, I'm probably going to have to use 2 inequalities. Anytime I have to use 2 different arguments, there's some sort of like capital N that makes one of them true, and there's a capital N that makes the other one true. And a common technique to get both of them to be true is to say, let me take this max of the 2. Okay? And are you happy with the logic of why that actually makes sense? Yeah, because as long as it's true for all of them past a certain point for this one, and true for all of them past a certain point with this one, all I have to do is make sure I'm at a number larger than both of those, or equal to the biggest of the 2. So that's a common technique you'll see. Anytime you have this list of inequalities that you all need them all to be true. Maybe said another way, in all of these proofs, one of the key things is finding the capital N. It may seem underemphasized because everything else we did took so long and it took so many different manipulations, but actually what was really critical was arguing that there exists a capital N. Why does that capital N exist at all? Like, why is there a point in the sequence such that some inequality is true from then onwards? And once we have that capital N, it's really powerful. So maybe it gets de-emphasized, but it's actually kind of the key to everything. And so anyway, we need both to be true, so we have to make sure that we're past both of them if you think of it as sort of going down the sequence. Any other questions before I erase? Okay, let's do an example that's quite similar to this. I don't know if it's overdoing it, so feel free to also move me forward. We will get to these questions in a bit. Anyone still writing here? No? Okay, actually, yeah, let's erase. So I think we're going to do just one of the tutorial questions, which was, it was tutorial for question 1C or something like that. Maybe someone can correct me, but it's like, suppose AN goes to 4, and they were telling you show 1 over AN goes to 1 over 4. By the definition. Okay. Can anyone verify that that was tutorial 4, question 1C? It was? Cool. Just make a little space, suppose. So anyone who didn't hear what I say, that's tutorial 4, question 1C. C. Tutorial 4, question 1C. And this again was, I thought, at least for me, I thought it was one of the harder of sort of one, I think we did A last time, and part B was also kind of similar to A, although we can talk through it if you want to have that afterwards. But this one's a bit funnier because you have to do something a little bit different. And we kind of saw the strategy in a harder setting where this was undetermined. Okay, so this is also like kind of a response to one of your questions where we could say at this point, we could say, well, in lectures we know that it goes to, if it goes to some limit, then 1 over the sequence goes to 1 over the limit. But now they specifically say use the definition, so now you have to do something different. But they should communicate to you what they expect, and if you're unsure, always ask. Yeah. All right, so again, so here's our rough work. Okay, we know that we have to look at this, right? We're hoping that we can kind of study this object and say, is this less than some epsilon? Okay, we're going to have to find a capital N and some inequalities and stuff so that this works. So what are we going to do? We're going to simplify it. Always want to rewrite it in the most useful form to us, which is going to again be just finding common denominator. So again, that's equivalent to, what did we say? AN minus 4 over 4AN. Okay, and I kind of did common denominator and I multiplied by -1 just because I want it to look like this. And just convince yourself that this is the same as this. Okay. And maybe in this more tangible form, it's kind of convincing that if I write it like this, like 1 over 4 A, and you may or may not want to write this down, this is up to you, times 1 over mod AN. And we want to show that that's less than epsilon. So notice I didn't do anything funny here. I just literally rewrote it. This is the numerator. It's sitting right there. I have 1 over 4, which I want to kind of group with the numerator. And then I have this other thing, 1 over mod an. So if you feel really comfortable with just manipulating with absolute values, just notice I didn't change anything. I just kind of grouped the absolute values slightly different. Is anyone lost at this stage? Just because I can talk through that quickly, it would be unfortunate to get lost there because we want to talk more. Okay, so for me, this is just sort of how I'm thinking about it in my head. It's like, this is some other thing that I have to deal with, and this is something that I can deal with. This is some constant times something I know how to deal with. I always know how to deal with stuff where it's an minus a number, because I know that an already converges. So I know that I can deal with things like absolute value an minus a number. I know some tricks. I'm not sure which tricks to use yet, but I know that I can go. That's as kind of a separate problem. And then there's this issue, this 1 over mod an that we've been kind of going on and on about. So notice, 1 over mod an appears. Use reverse triangle inequality. Okay? And what do I want to use it? How do I want to use it? I want to use it with something I already know. And what do I know already? I know that mod an minus 4 is less than some, we can use c again, some c, which is less than or equal to mod an minus mod 4. Okay, so this is me just applying the reverse triangle inequality, and this is me saying that for some c, I can make this whole thing kind of work, and I haven't put it together carefully yet, but this is what I'm doing in my rough work. Remember, this isn't me writing my formal proof yet. This is me just asking myself, what kind of inequalities can I make, given what I know? So again, we were talking about when I see 1 over mod an, I want to find, if I want that to be less than something, so that I can generate this statement up here, then what I'm really doing is if I want this to be less than something, I need to find mod an to be greater than something. If 1 over mod an is less than something, mod an needs to be greater than something. The reverse triangle inequality helps me. And you can convince yourself that this is equivalent to saying that 4 minus c is less than mod an. Well, let's not say equivalent, let's say this implies. Okay. I skipped a few steps. Maybe I can put them in over here. I'm not sure if I went too fast. So we said that minus c is less than, let's also not say equivalent, but let's say implies that minus c is less than mod an minus 4, which is less than c. Okay? Remember what we did last time. We know we want to look for an inequality involving mod an. Okay? So we need to get rid of this absolute value. Okay? I used the reverse triangle inequality to get me an object that involves mod an, but now I need to get rid of this absolute value. How do I do that? I write minus c less than mod an minus 4 less than c. So whenever I have absolute value of something less than a number that's positive, I have minus that number less than what was ever inside the absolute value less than c, less than that number. Okay, so sorry, I added an extra step because I thought maybe I went too quickly. So we know this, that implies this, which then implies this. What did I do to get this? I just added 4 to the whole thing, but in particular I only care about this part. I don't care about what this is less than. Everyone happy so far? Okay, so this is looking similar to the other one, but we have actual numbers in some of the places. Okay, so we can just do one more, And that implies that 1 over mod AN is less than 1 over 4 minus C if C is, C is greater than 4. Sorry? Less than 4. Thank you. And in fact, should be careful because it can't be, oh yeah, that's fine. Okay, so if C is less than 4. Thank you, I'm glad that everyone's paying attention, I can see. Okay. All right, so then what do we want to choose C to be? We could choose it to be 2, choose it to be 1, choose it to be 3. Probably 3 is great, right? If we choose C to be 3. You get this inequality is less than 1. That's kind of nice to write down. But I really want to show you that you can make a choice. But how do you know where the choice is? Where does the choice come from that's in the textbook? Where does the choice come from that's in the lectures? You really need to think about, what did I do? I divided by something. I need to care about whether it's negative or not, because it'll mess with my inequalities. So I'm going to choose C to be 3. So let's kind of summary. AN goes to 4 implies there exists an N1 such that N greater than N1 implies that 1 over mod AN is less than 1. Okay, since I said this could be true for any C, as long as C was less than 4, I'm just going to choose C to be 3. And so the whole story that I put together just looks like this. Is anyone getting a little lost with the whole choosing C question? Because now is a good time to ask. Okay, so we've dealt with the one part of what we were looking at, and now we just need to do kind of the other part. Okay, so and so I'll think of this still as my rough work. So recall we're looking at mod A minus 4 over, AN minus 4 over AN times 4. Okay. So AN goes to 4 implies there exists an N2 such that N greater than N2 N greater than N2 implies that mod AN minus 4 over 4 is, let's say, less than epsilon. Because remember, we were originally looking at this, and we want this whole thing to be less than epsilon. We've kind of demonstrated that there's an N1 such that this part, the 1 over mod AN that's here, is less than 1. So now we just have to deal with the AN minus 4 over 4. And you know safely that just if AN minus 4 converges, there's some way to make this work. Are you happy with that? That's just saying that, well, we know this converges, so we can always make this less than some real number. So we know that any constant times this, we can also make less than some positive real number that we care about. And then do we want to write it out carefully, or are we kind of happy at that point, or shall I write out? I think it's generally a good exercise for me to write out the whole thing. Okay, yep. There's a question. So let's just write the whole thing out very carefully.
If they do give us the actual sequence AN, and maybe we find that the sequence's first term is left 1 and it's an increasing sequence, can we just remove the sequence and say AN maybe -4 over AN4 is less than AN -4 over 4, because that is like a positive, it's going to make that whole absolute value smaller because the
Smaller and
denominator
smaller.
is bigger.
It's increasing. That's a good question. Let me think about that for a second. It sounds plausible. I just don't want to tell you yes and then it's wrong for some reason. Okay, so you're saying that AN is always increasing.
Or maybe like just find
And so then one-
AN is always greater than 1. And it's, you know that it's always positive, and you know that every single term is always greater than 1. So there's no way when you divide by it you get anything that will make the whole thing bigger. So you can
I see what you're saying. I think we'll make up an example in a second. I'll write this out and we'll make up an example just to test. I see what you're saying. It sounds right. I just want to make sure that there's not something I'm missing, so I'll think through it carefully in a sec. But I get what you're saying. Does everyone understand what she's saying? She's saying, like, perhaps if this is getting, if AN is getting bigger, or at least that whole 1 over AN is less than 1.
Yes.
Yeah, the 1 over AN is less than 1. Then you can just kind of get rid of it. That seems right. But yeah, we'll do an example in a second. Just check. Yeah. All right, so let's just write this out carefully. All right. So proof. Always kind of write the word formal. As I said to others last week, you don't need to write the word formal. I'm just kind of writing it in these workshops just to kind of really emphasize the difference between rough work and formal proofs. So formal proof. Let's just write it this way. For all epsilon greater than 0, there exists an N1 such that such that little n greater than n1 implies that 1 over an mod is less than 1. Okay? Also, it's kind of weird that I put the for all epsilon there, but it's fine if it's at the front. This whole statement is true for any epsilon we choose. Also, there exists an N2 such that n greater than that capital N2 implies that mod 1 over 4 times an minus 4 is less than epsilon. Okay? Then you can write, then if n equals max, because I want both conditions to hold, and I'm going to erase a little bit here. So then if this capital N equals the max of that N1 and that N2, N greater than capital N implies that's right, implies the next line implies that mod an minus 4 over 4an is less than, we had a, do we have a less than or equal sign there? Okay, hopefully not. All right. I'm concerned about that for a second. Yeah, sorry. I hope I didn't leave this out somewhere important, but I think we agreed that this is a less than or equal. Does that make sense to everyone? Because when we were using the reverse triangle inequality, so I don't know if I left that out earlier. Please check me that I apologize if I did. The point was we were using the reverse triangle inequality, so when we went to the left, we had a less than or equal. So we had something like we had something like 4 minus c less than or equal to mod an. It should have been less than or equal to mod an. 4 minus c less than or equal to mod an, because we used the reverse triangle inequality, and the reverse triangle inequality is a less than or equal. Then when we divide on both sides, we still have a less than or equal. So when we say mod 1 over mod an is less than or equal to 1 over 4 minus c. Everyone okay with that? Yep.
We did the in-between step of, I think it was minus C on one side, C on the other side, and then mod A and minus 4, those all equals 2 sides.
That's true, that's why it wasn't. Okay, all right, then everything I just said was wrong. Let me just check quickly. Can I take your notes? Yeah, I think what you said is good. Yeah, that's where we lose the less than equal. Okay. Sorry, I apologize for that. All right, so to correct one more time, I'm sorry if you now drew it in, because that makes it much harder to write. It's at this moment where I thought I had forgotten something. There is no less than or equal to there. Why? Just do it over here. If you check your notes, we had something like mod an minus 4 mod less than c. This was a strict less than. It's actually still true with the less than or equal, but it's fine. So we had a strict less than. That was equivalent to minus c less than mod an minus 4 less than c. Strict less than. So there's a strict less than everywhere. So I apologize for that. I just made you add something that you didn't need. Sometimes it's late in the day. Okay, so anyway, we were here. So if I take n, capital N to be the max, then both conditions hold. Okay? So that means when I'm studying this original thing that I cared about, okay, I have that this is less than, I want to get rid of the 1 over mod an, which is right there. And since we said it's less than 1, I just get to write this. Over 4. Okay? Because all I'm doing is I'm just saying I can think of it as a 1 over mod an times this. Okay. And then this, since the other condition also holds, I already know that 1 over 4 times this, or this divided by 4, is less than epsilon. Okay? Both conditions hold because we are looking at all the little n's that are bigger than capital N.